Hello everyone and welcome back to Meaning Analytics. In this video, we are just continuing with our series that we started earlier. So in the previous video, where we were comparing the different classification algorithms, so we were able to compare those classification algorithms and come to a conclusive ending. So if you haven't watched that, you can also create time to also watch that analysis. So for this, again, we are just continuing with that. And for this case, we are dealing with the diabetes. So we are going to analyze different types of classification algorithms and ultimately select the best classification algorithm by which we are going to be using to build a model that will enable us able to diagnose diabetes. So basically, that's what we will be handling in this analysis. And before we get started, if you're new to this place, please consider subscribing. We are welcoming you to this wonderful community. Hit that notification bell so that you never miss any of our video updates. You can also leave a comment behind because we like hearing from you. So without further ado, let's get started with today's analysis. So as usual, I'm going to start by importing the Python libraries. I will be importing the pandas, NumPy, matplotlib, as well as the Seaborn libraries. So I'm going to execute this cell so that we import these libraries. So after importing the libraries, we then move forward to importing the dataset onto the Jupyter notebook. So for importation of the dataset, I'm going to be using the read CSV function. This is a function from pandas. Then inside the brackets, it's basically the file path as well as the file name. And I'm going to use the head method to display the first 5 rows of our data frame. So basically this is our data frame, and as you can see, we are having different attributes. For example, gender, age, BMI. So when I say attributes, essentially what I'm referring is the columns in our data frame, and inside the columns we are having the data entries or the data points. Okay, so after importing our data, then we can move on to the next step, which is the data summary. So basically I want to have a quick overview of the data that I will be handling for this analysis. So for the data summary, I'm going to be using the info method. So data summary. All along, I will be using comments. They will be guiding you in whatever steps that I will be taking. So for the data summary, I'm going to be using the info method. So for the info method, we are getting a description of our data frame. And from the description, we are able to get information about the number of entries in the data frame. We're also obtaining information about the number of columns. As you can see, we have a total of 18 columns. And then we're also getting information about the null count, which is quite important because under this, we are able to identify the columns that are missing values. And also, we also get information about the data types. So for the data types, these are the data types. This represents the type of data in the respective columns in our data frame. Okay, so from the look of things, we can see that our data frame is quite okay. We are not missing values, and from the look of things, I can see either we are having floating point numbers or integers from our data frame, and that is what is represented in the respective column. So we don't have a lot of data cleaning steps that we are going to be handling. So moving forward, we might maybe check for duplicates. So we don't have missing values, so we can check if our data contains duplicates. So with that, I'm going to use the duplicated method. So I'm going to say we are going to checking for duplicates. So checking for duplicates. So that's what we are going to be doing in this step. So when checking for duplicates, I'm going to use the duplicated method. So this I'm going to use the duplicated method, and inside the brackets I'm going to pass in arguments, and for the arguments then I'll use a boolean value false. Then outside the brackets I'm going to sum. So what essentially when we pass the argument keep false, we are going to label all duplicated rows in the data frame as true, and after that we are going to sum all the true values in our data frame. So essentially it will print out the total number of duplicated rows in the data frame. But if we get a value that is less than 0, or we get 0, or a value that is 0, then that means that we don't have duplicates in our data frame. So when I execute this, you can see we are getting the output from that is 0. Then that means we don't have duplicates in our data frame. Another thing that we can, since we are going to perform a classification exercise, then there's one thing that we didn't tackle very much during the previous video, but in this case we are going to in our target variable, that is the column or the attribute diabetes, because remember we are going to build a model that will enable us to predict if a patient is having diabetes or not. So therefore diabetes forms a very important column and that column is known as the target variable. So I'm going to check for class imbalances in our target variable, class imbalance. So definitely when we check for class imbalance, we are checking class imbalance on the target variable. And class imbalance generally is a situation that occurs in classification tasks where one or more classes in the target variable, where one class has significantly more or fewer instances than the other classes. So definitely when in other words, one class is underrepresented while another class or classes are overrepresented in the data set. So that's what we are going to be determining under this section. Obviously, class imbalances have a significant impact for any machine learning, for any classification machine learning models, as it majorly impacts the model performance as well as the accuracy. So with class imbalance, we need to be very careful with the metrics that we are going to be using while evaluating our model. Okay, so for the class imbalance, we're just going to count the values in the target column. So I will create a variable diabetes, and for diabetes, then from our data frame df, we are going to definitely we are targeting the column diabetes, and in our data frame, then we are just going to count the values of the different classes. So value counts, then we reset index. Okay, then after this we can then just print. So it's supposed to be index. So when we execute this, we can see we are getting a new series, and this series is a representation of the classes in the target variable diabetes. So you can see we have the class 0, which definitely represents the patients that did not have diabetes. So when we look at the count, we see that we have a total of, in our data set, we have a total of 3,000 patients that did not have diabetes, while 1 represents the count of people or patients or individuals that did have diabetes. And you can see we have a total of 1,303 individuals were recorded to be having diabetes. So I'm going to represent this information using a pie chart. So for the pie chart, I'm going to use the matplotlib library. So plt.py to represent a pie chart. Then I'm going to recall the data frame, and my values will come from the column count. Okay. Supposed to be square brackets. So supposed to be square brackets. And for this, then for the labels, this will be coming from the column diabetes. So this will be the labels. In here, we just be using square brackets. So after that, we can then provide the title for our pie chart. So our title will be a class distribution. We display our plot. So plt.show. So when we execute this cell, you can see this is the output that we are getting. So we have a pie that is visually representing the class distribution. And for the class distribution, as we had alluded earlier, yes, that there is class imbalance in this case. So for class 0, we have 300, as we saw, we have 3,000 instances representing about 69.7% of the all instances. So this will be the majority class, while for the class 1, we had a total of 1,303 instances. This represents about 30.3% of all instances in our target variable, and we will label this as the minority classes. So we have determined that our data contains class imbalances. So we will move forward to now starting the process or the procedure of building our modules. So the algorithms that we're going to be applying in this case will be the random forest, the XGBoost, the lightGBM classifier. I will also use the K nearest neighbors classifier, the AdaBoost, and maybe the CatBoost if we have time. So I'm going to give a list of the algorithms. So in general, we have a total of 6. So I'll do away with 1, CatBoost. So these are the algorithms that we are going to be comparing and see which amongst this is best or is ranking best in terms of accuracy in making this a classification. So the first thing with that is that I'm going to import the classification the random forest, the AdaBoost, the K neighbors classifier. We also have the XGB classifier as well as the LGBM classifier. So after importing these classifiers, we then move on to the step. The next step also, I will import the pre-processing modules. These include the train test split as well as the standard scalar. And so the pre-processing modules, so those include the train test splits. So when we are trying to split our data into the training set as well as the testing set, we are going to be using the train test split. And lastly will be the model evaluation metrics. So these include the classification report, the accuracy score, the confusion matrix, precision recall curve, as well as the ROC curve. So these are the evaluation metrics that we will be using to grade our models and determine which model is actually performing well in this classification. So moving forward now, in another step will be about defining the features as well as the target variable. So we'll be defining what are our independent as well as the dependent features. So for this case, our x will be, I will use x to represent the features. So this will be the dependent variables. And for the dependent variables, actually I will be using each and every attribute in our data frame as the dependent variable, because we are trying to predict the abilities. So for that, every other column will be our dependent variable. So to make our work easier, instead of creating a list of all those columns or all those features, I'll just drop the target variable from our dependent features. So for that, df.drop. So I'm using the drop function. So from the drop function, then we specify the columns that we are going to drop, and that is the column diabetes. So that's the column that we are going to be dropping from our dependent features or variables. So we can just again use a comment here and say defining the dependent variables features. Others will call this as features. So those are the dependent variables, and for the independent variable, that is our target variable. So we just say target variable. The target variable, I'll use lowercase y. Then this will be just the column that we dropped in earlier. So diabetes will be our target variable. So when I execute this, so we are getting an error. So column, we execute this, we can see then we will have defined what are our dependent variables and what is our target variable. So whenever we call x, we are calling our dependent variables, and whenever we call y, what we are trying to call is the target variable. So what we are trying to predict. Then we can move on to now splitting. We are going to split our data into training sets as well as testing sets. So for splitting, we will be using the function train test split. So I'm going to create the variables that will be storing the split data. So start with the xtrain. So xtrain, xtest, xtest, then ytrain, ytest. So xtrain, xtest, ytrain, ytest. Then we call our function train test split. So train test split. Then after this, x, y, so our dependent features and the independent features. Then our test size. So for test size, I'm going to use 0.25 for our testing, while 75% will be reserved for training. And for the random state, this one I'll use 111. So we are getting an error, so it's supposed to be random states. So when execute this, we will have now split our data into the training and the testing set. So after splitting our data, we can then perform the standardization. So by this, we are going to scale our data. So scaling. So when scaling, so the first thing is that I'm going to initialize the standard scaler. So initialize the standard scaler. So definitely here we're just creating an object of the standard scaler. So I'll first create a variable scaler, then create an object for that. So standard scaler. So after we initialize the standard scaler, we can then fit the scaler on the training data and transform it. So fit the scaler to training data and transform. So I'll create a new variable for xtrain scaled, then scaler dot fit. So we are fitting as well as transforming. So we are using the fit transform function from the standard scaler. So fit transform. So we are, and remember, we are transforming the xtrain data, so our training data. So I'll just paste it inside here. After we have transformed our training data, we are going to be using the same scaler, but for this case, we are going to now transform the testing set. So transforming the testing data. So again, x test scaled. Then here we can recall the same scaler. Then we transform here we are transforming our testing sets. Okay, so by executing that, we will have transformed now our training as well as the testing set. And also remember, when I'm doing this transformation, as you can see, I'm only targeting the features. So I'm not transforming by any case the target variables. Okay. So after that, then we start. We have cleaned our data. Now our data is ready to start the process of building this machine learning model. So I'm going to start with the k-neighbors classifier. So for the k-neighbors, so when building this classifier, the first thing is about creating the k-neighbors classifier. So we're creating an instance of the k-neighbors classifier. So knn model. Then we are creating an instance of the. So we are creating instance of the k-neighbors classifier. So after that, we can then fit the model to the training data, then fit the model to training data. So here again, I'm going to recall. So knn model, just paste it here. Then here we are fitting, so fit. Then we are fitting the xtrain scale and the y train. So essentially, what we are instructing our model is that we are allowing our model to learn the relationship between the our features as well as the target variables. So after learning this, the pre-existing relationship, we're going then to use the same model, but now to make our predictions. So making predictions. So when making predictions, again, I will recall the model. So I'll just copy this, paste it here. Then we'll create a new variable. So ypred for the k neighbors classifier. So knn model dot predict. Then we are making predictions on the x-test scale. So after making our predictions, then we now move on to the most important step in this analysis, which involve model evaluation. So under the model evaluation, now we are going to see how our model is performing with respect to the different types of evaluation metrics that we are going to be applying. So the first will be about the classification report. I'm going to first evaluate our model with respect to the classification report. So classification report. So for the classification report, I'm going to use the classification report function. I think we already imported the module. So print, so classification. So classification report. Then we are evaluating our model against the true predictions. So that is the y-test against the predictions from our model. So that is ypred knn. So we are going to execute this cell. So as you can see, this is the output from the classification. So as you can see, we have the metrics precision, recall, as well as the F1 score. So just a brief explanation about these metrics. So when we talk about precision, this is all about being precise or accurate in the positive predictions. So that means that if we are going to deploy our model to make predictions, precision measures how accurate our model is making those predictions. And when we look or talk about the recall, this is about our model capturing as many positive instances as possible. The F1 score is a way to balance both the precision as well as the recall for a more comprehensive evaluation of our model's performance. So remember that there are instances where the precision will be very important. There are also instances where the recall will be very important when evaluating the model, as well as there are instances where the F1 score will be most important when evaluating your model. So in this case, for the class 0, where class 0 represents that these individuals did not have diabetes. So with the class 0, we have a precision of about 93%, a recall of 99%, as well as an F score of 96%. So in other words, this suggests that when the model predicts the negative classes, so that class 0, it is very accurate at about 93%. Moreover, it's very effective in capturing the majority of the actual negative instances when doing the prediction. You can see we are getting a high value, 99%, resulting in obviously in a high F1 score of 96%. So generally, we can say that our model is performing exceptionally well in identifying classes of or instances of class 0. Okay. So now let's move on to class for class 1. So when we look at class 1, this definitely we are making predictions in the sense that these patients or these individuals did have diabetes. We can see that we are having a high precision of 98%. but we can see that we have a decrease in the recall of 0.83 and giving an F1 score of about 90%. Generally, we can say that in terms of classifying the class 1 instances, our model performs well in identifying the positive instances, but we can say that it's leaving some, or it's giving us a room for improvement with the recall. Okay, so when we try to improve our model, then definitely we see where we can try to improve our model. Okay, so the next evaluation metric will be the confusion matrix. So for the confusion matrix, we're going to use the confusion matrix function. So again, I'm going to print. We're going to be repeating the same thing. So I'll just copy this. Then instead of classification report, we're going to change that to confusion matrix. Then when we execute, oops, we are getting an error. Confusion matrix supposed to be okay. So from the confusion matrix, definitely when we look at the confusion matrix, what we are trying to see is how our model is making those, or how our model is accurately, or how our model is correctly or incorrectly making those classifications. So for the confusion matrix, we can see that from our model, we have a high number of true positives. You can see that 28 to 86. So 286 is the count of the true positives, indicating how our model is indicating the ability of our model in identifying the true positive instances. While for the true negatives, 725. So for the true negatives, these are the instances where the model predicted that a patient did not have diabetes, which in real sense that was the case. And for the true positive is the instances where the model actually predicted that the patient did have diabetes, and that was the true case. And for the false positives, we can see we are getting 7. 7 represents the count for the false positives. So by this, it indicates the instances where the model mistakenly predicted a positive class, and in actual sense, it was supposed to be a negative. And for the false positives, we have 58. So 58 represents the count for the false negatives, and the false negatives suggest the instances where it missed the positive cases. So in real sense, it predicted that our model, it predicted that these patients did not have diabetes, but in real sense, these patients did have diabetes. So that was all about the confusion matrix. Now we can see how the classification indeed took place. So the other thing is about the precision recall, as well as the receiver operating characteristic curves. So also for when evaluating our model, we can also use the precision recall as well as the receiver operating characteristic curves to determine or evaluate the model performance. And oftenly, the choice between either the precision recall or the ROC often depends on the specific goals of the classification task. So definitely, when we are trying to build a model, you have a goal or an objective that you're trying to achieve. And to be able to evaluate the model in such a way that you are meeting those objectives, that's where the PR and the ROC curves come in. And when we are using this in terms of evaluating a model, then the the term false positive and false negative also come in handy. You should be able to explain the false positive as well as the false negatives. We saw that the false positive occurs when the model predicts that an individual has diabetes, but in reality, that individual does not have diabetes. And one of the things that you need to understand about the PR and the ROC curves is the trade-off that we are trying to achieve when using these curves. So for the positive, for the false positive, we are predicting that this patient is having diabetes, but in real sense, or this patient does not have diabetes. So definitely there are consequences for us making that prediction. And what are the consequences? The consequences is that this patient will undergo further medical interventions, which in most cases are unnecessary. Okay, so what is the effect of the converse effect? When we are looking at the false negative, you can see our count for the false negative was 58. False negative occurs when the model predicts that an individual does not have diabetes, but in reality, that individual does that individual does suffer from diabetes. Again, there are consequences when we make this prediction. In one way or another, we are delaying medical intervention, which in future it can potentially result in serious health consequences. So those are the things that you need to be conversant with when dealing with the PR as well as the ROC curves. Okay, so in this case we are going to be plotting those. So under this, the first thing that we are going to do will be about predicting the probabilities for the positive class. So we are going to predict probabilities of the positive class. Here again, I just create a new variable. So y probs, then knn. Then I will recall the model. So knn model. And then use the predict proba function. So predict proba. So basically we are predicting the probabilities of the positive class. Then X test scaled. So I think when doing these predictions, we are actually targeting, I think it's between 0 and 1. So I think that's why we are including this. So then after predicting these probabilities, we can then calculate both the precision recall curve as well as the ROC curve. So calculating, I think calculating the PR as well as ROC curves. So here precision recall. Then we'll use the precision recall curve function. So precision recall. Then here we supply our data sets. That will be the y test as well as the variable that is storing the probabilities for the positive class. And for this one is for the PR, and for the ROC curves, remember we are dealing with the false positive rate as well as the true positive rate. So for the ROC curve, we are dealing with the false positive rate as well as the true positive rate. Then so you can say ROC curve. Then here you can just repeat the same thing using the same. Just copy this and paste it inside here. So after this, we can now calculate the area under the curve for the precision recall curve as well as the ROC curve. For this, we are using the awk function, and for the PR curve, we are using the recall and the precision. So it will be precision against recall. And for the rock curve will be true positive against the false positive. Then after this, we can then plot the curves by themselves. So with this line of code, we are going to plot the precision recall curve. So we are setting the figure size. Then since there are two plots, we are using the subplot function. Then specify our values. Then color will be dark orange for the precision recall curve. Then line width will be 2. Then we supply our X labels, the Y labels, title as well as the legend. And we are also repeating the same for the rock curve. Then we are going to execute this cell so that we do get our output. So from our output, we can see we have the precision recall curve as well as the receiver operating characteristic curve. And when you look at the area under the curve for the PR, we are getting 0.96. And for the rock curve, we are getting again 0.96. So we are finding similar values for the two plots. So as we had said earlier, we saw that the precision recall curve and the receiver operating characteristics curve are both very important when evaluating the performance of our classification model. They are particularly very important in different contexts, especially when dealing with class imbalance. So in cases where there is a significant class imbalance, so that means one class has many instances than the other, the PR curve, as we are seeing, provide insights into how well the model performs in terms of the precision and recall, and it gives more focus on the positive class. So having a high area under the curve for the PR curve suggests that the model can effectively identify positive instances even in presence of class imbalances. So we are getting an area under the curve of 0.96. Then that means that our model is performing well to distinguish between these two classes, irrespective of us having class imbalances. And for the rock curve, this one is also important in terms when we are talking about class imbalances. The rock curves are not as informative as the PR curve. This is because the true negative rates can be very high even if the model is not performing well in identifying the positive instances. That means the rock curve will be misleading in imbalanced scenarios where the performance on the majority class dominates the metric. Again, remember, this was a comparative analysis, so we are trying to compare the different algorithms to see how they are performing with respect to our data. Using what we have learned, now we can do now the comparative analysis, compare the k-neighbors classifier with the other algorithms. So to easen our workload, I will be using loops help us achieve our end goal as quickly as possible, and also reducing our the lines of code that we are going to be writing. Okay. So for the other classifiers, we start by defining the classifiers. I'm going to create a dictionary, and in this dictionary, we are going to classify. We are creating key and value pairs. So for our key, it will be the classifier name, and our key will be the name of the values, while the value will be the instance of the classifier. So as you can see, we have the random forest, adder boost, xg boost, cat boost, as well as the lgbm classifier. After creating our classifier, we are going to iterate over the classifier, and while doing this iteration, we are going to fit the model to the training data, then make predictions on the test data, and then print the classification report for our models. So by this, we are going to compare how to the classification report. So when I'm getting an error, that boost is not defined. So we can just do away. Can remove the cut boost for now. So let's work with these 4. So when we execute this, this is the classification report for the different classification algorithms. So when we look at the precision, when we look at the random forest classifier, we can see that it has a good precision for both class 0 and class 1 instances, 0.96 and 0.94. So those are quite high in terms of the recall, also in terms of the precision. Also for the recall, again, we are getting good scores, 0.97 for class 0 and 0.91 for class 1. So having a better precision and recall will also give us a better F1 score. So we can see 0.97 for class 0 and 0.92 for class 1. Also, another thing that we can see that we saw earlier is that the precision for class 1, you can see that when we look at the recall, it drops for the random forest, similar to what we saw earlier. Okay, and this model, but it's making this model has a 95% accuracy. Also, when we look at the other boost, we can see that we're also getting good precision scores for both class 1 and class 0. Again, the recall values are quite good for this classifier. For the XG boost, we can see for the XG boost, we can also see how the model is performing. We're also getting good precision scores, the recall, as well as the F1 score. Also, we can see for the class 1, you can see that the recall is slightly less than the precision, similar to what we saw earlier. Okay, so for the XG boost, again, these are we also getting good scores for that, as well as for the LGPM classifier. So generally, we can say that our models are performing quite well. So this was for the classification report. Then we can also perform the same. So we just repeat this. But for this case, we are going for the confusion matrix for these classifiers and see how they are performing. So for the classifiers, again, we're just repeating the same thing, using a for loop, then fitting the model to the training data. Then we are making predictions and then printing out the confusion matrix. So when we execute this, this is the output that we are getting. So earlier on, we saw from the analysis, we saw that so when you look at the confusion matrix, we can see that the XGBoost classifier is performing quite well because we are getting almost a higher number in terms of making the true positives, 315 for the XGBoost, 315 for the other boost. For the confusion matrix, for the random forest, you can see it is 313. But when we look at the false positives, so the count for the false positive is 16, which is the least among the other classification algorithms. LGPM classifier follows at 17, then 21 for the random forest and 22 for the other boost. Okay, so depending with your objective, so I'm also going to use the same to now plot the precision recall curve as well as the rock curves. Also here we started by defining the classifiers using a dictionary so that we can be able to pair the key value as the key and value pairs. Then we set the subplots because we are going to print a grid. and this grid will be about the PR curve as well as the ROC curve for the classifiers, and they will be side by side. Then again, we use the for loop to iterate over the classifiers, then make predictions, then simultaneously plot the precision curve as well as the ROC curve. We execute this cell. Charts are looking. So from the random forest, we can see that we are getting a PR curve. For the area under the curve is 0.98 for the random forest, and for the ROC curve is 0.99. So we can also see that random forest is performing quite well in this analysis. For the ADA boost, then we can see the PR curve, the area under the curve is 0.98, then 0.98 for the ROC curve. For the XG boost classifier, we can see that the area under the curve for the precision recall. For the precision recall, for the XG boost, you can see that 0.98, and for the ROC curve is 0.98. Okay, and for the LGBM classifier, you can see again 0.98 and 0.99 for the ROC curve. So earlier on, we saw that when dealing with class imbalance, then the best classification algorithm, or you're going to focus more on the precision recall curve. The ROC curve for the K neighbors is 0.96. Then for the random forest is 0.98. For the ADA boost is 98, and then 0.98 for the classifier for the XG boost, and also 0.98 for the LGBM classifier. Look of things, all PR curves have an area under the curve of 0.98. The goal for your analysis is to predict with high precision patients with diabetes. And when we look at the precision, the classification report for the different algorithms prioritize the models that have high precision for the positive class. That means the diabetes cases. So precision will be the metric that measures the accuracy of the positive predictions. So when we look at the random forest, we can see it has a precision of 0.94. When you look at the ADA boost, it has a precision of 0.93. And when you look at the precision of the XG boost, is at 0.95. And when you look at the precision of the LGBM classifier, for the positive cases is 0.95. So for this case, if I'm going to select the best model that we are going to build this, the best classifier to build this model, I will select either the XG boost as well as the LGBM classifier, simply because they are standing out with the highest precision for predicting patients with diabetes. Okay, so I'll select those either of those two while building the model for predicting diabetes in different patients. Okay, so I think by now I think we have reached the end of our analysis. So earlier on, our objective was trying to select the best algorithm given a set of data to build the models with respect to the different classifiers. And after that, we were able to select the best algorithm for this case, and we saw as either the XG boost or the LGBM classifier are appropriate to build a model that can be used to predict patients with diabetes. And before I sign off, so if you are new to this place, please again consider subscribing to our YouTube channel. We are welcoming you to this wonderful community. Hit that notification bell so that you never miss any of our updates. So until next time, bye bye.